Okay, hello guys. So I'm gonna just quickly run through the finalized graph for the WFC solver. So this is the building generator, and it makes the points which we copy the named geometry to. So what this solver is doing is receiving a geometry input, converting it into points on a grid, 3D grid, and then naming those points. This HDA doesn't actually place any geometry, it just creates the points and their orientation so that we can replace them with meshes. So I've made this very quick shape, and I've given it a more recognizable silhouette so that we can try and see that in our points, because bear in mind that we are just going to be looking at points, which might be a bit hard to focus on. There you go. That's going to be quite a recognizable silhouette. So normally this would be our geometry input, but we're staying in the HDA for now. So let's go through. So first we need to make this into a grid. So we have our box combination node. Now we can see our tool spire, and if I put numbers on, we'll be able to see them a little bit better. So we have our tool spire, and then we've got our larger lower cube, and you can see that it's kept kind of the order by using our two different shapes. So we've got 0, 1, 2, 3, and 4. And if we look at our initial shape, is this? That is 1, 2, 3, and 4. And then we've got 5, 6, 7, 8, 9, 10, and that's the larger section. So let us look at the geometry spreadsheet. So right now we're basically empty. We have just got points with their location. They have no information except their number. So we've got 8 points at the moment, 0 through 7, and they have no attributes except for their location. So if we go through these nodes, we'll start to see attributes build up, and we use those attributes to make the next attributes. Okay, so let's get to the first most important node. So this takes each point, it also reads its neighbors, it compares that to a spreadsheet, and it basically says, okay, this point can be any of these meshes, and I'm gonna pick one. I'm gonna randomly pick one from a random number that I've also given it, and let's say we're at near the bottom of the building, and we say, okay, it's gonna be wall 2B, this one here, and now that's started our WFC. The WFC is something that's used in procedural generation to get a more controlled generation. From my understanding, it is like following rules while randomly generating. So I've drawn a little example here. So right now we have a square, and the square has 4 edges that each have a color. So blue, green, red, and purple, and we need to fit this square 4 times into that grid. Now there are a lot of different combinations. We're restricted to the rule that a color must touch its own color when we're arranging it. So let's say I make a choice, and that choice is, I'm going to put this one here, okay? And then if I make another one, it means that this which could have been anything before. I could have chosen to start with this one and have it be any rotation of this square, but now it needs to be a green on the bottom. I don't use that much paint. How do I rotate? You get the idea. I'll just draw it. So this bit has to be, there you go. This bit has to be green. This bit needs to be red. And now, let's say we had a second option for our cubes, which was just a different jumbled up version. So we've got green, and then purple opposite, and we've got, is this going to be the same thing? Wait, let me purple here, red here. So this is the same. We've got matchups. That's going to be confusing, isn't it? Okay. We'll have purple adjacent, so that we definitely can't have the same combination. Sorry. There you go. Okay, so now let's say I'm using this template for this one here. It means that this one has to be purple, this one has to be green, this one has to be blue, and you can see how now if this grid was 100 times bigger, how we would end up getting what would look like a random organization of these blocks, but it is in fact driven by rules, and that rule is these colors need to match. Now, I think if you didn't get that analogy, sorry, a different analogy would be maybe like Lego bricks. So you can't put a stub end on the receiving end, stub end on each other. They need to go to a receiving end. So these are our rules, and let's say we have okay, so let's say we have a connection here. Now this connection connects with this connection. So if I've placed this wall and this direction has this one, we only can choose a wall where it has the same receiving end here. So we need a CF44 underscore 0 to match with our CF underscore 0 IN. Yeah, so I'm not going to go too much into the spreadsheet, but these are the rules that our HDA is using in this Python script. So if I quickly just go over the sections, so we've got okay, so we can see our geometry spreadsheet here, which has our new attributes that have been made. So this receives our points from here after they've received their neighbor's attribute. Then we get a randomly generated number from this attribute wrangle, and then we get and that random number is being projected so that it can be referenced in here. And then we have the embedded JSON, which is our edXL, and you can see how we've got our all of our information here in a nice long hard to read way. Okay, so let's just quickly go through this. I'm not sure how in depth to do it, but so we are importing our random number and our JSON file. We are then setting a lot of our values. So these names aren't they are basically just ways of referencing numbers in other points of our code. So let's say our number generated is 1. We then tell pattern connector to be 1. Then whenever we need to reference that number 1, we type pattern connector. And that's because if that number changes to 2, it won't make a difference in the code. So we are taking our all of our information in, which is a mix of pre-chosen like strict rules, random generation, and then what's created by the user of the tool. Now another point is, this is where you have the choice to change your modular kit. So if we wanted to use a different modular kit, the way that we're doing that is by going into the edXL, and because all of these naming conventions are arbitrary. They're for this specific I don't know what you would call it, run. So this is just how they're being referenced in the code. So you could change this. It would just mean you'd have to change it in the code as well. Now, if you change these naming conventions here, that's okay. So let's say you have a modular kit and you've got different naming conventions. You're going to have to rename something for it to work. So you either make your own Excel sheet with your own naming conventions, or you do what I did, which is make a modular kit with the correct naming conventions just off the bat. So what else? We, after setting our references, we then go into our functions. I don't know, would you call these references or parameters? Okay, we jump into our functions. Now each function is getting a point direction, and basically it's chosen one and said this is what that piece can be, and then it reads its neighbor and says, okay, well, you are now reduced to this list of 3 different meshes. Now we can randomly pick one of those as well, and then it reads their neighbors and it spreads out. Now if I was going to change, because bear in mind this is from the tutorial, so if I was going to change this code and try and improve it, I would change this error message. So we have, what happens if you get to a point where you can't make a match? There's literally no options, but you get an error, and then you have to start again. Now that error might happen more often than not, and it would be good to have a string print to tell me which point caused the error, because then if I'm getting that same point multiple times, it might be not about how it's being randomly assigned and just a coincidence, but actually something that needs to be addressed. Now we can write something. I won't do it now, but we can write basically a mismatch, which tells us it will manually print a string, or it will promote it to here, so that we can get up. So we've already got one, so we've got the error and it says there's none. There's no errors, this is fine. But if there was an error, it would just say, yeah, there is, and we wouldn't really know what's going on. So if we were able to print maybe a more precise, okay, it was this point that caused the error, we tried looking for this match and there wasn't one, then that might mean, okay, well, I need to make more meshes that have that match, or I need to make more variation for the other points, so that that error is less likely to happen. Okay, so let's move on. You might have noticed that there's only 8 points. There was only 8 points, now we've got 11. 11 points that this is running over. This house is not going to be made from 11 modular pieces. It's quite a large house. So what's actually happening is these are the center points of cubes. The reason that we're doing it this way is because if we had a point per corner of per cube, we're going to have a lot of overlap, which isn't necessary. So instead, if we do the center of each cube and then only add points where we need to, and then removing points that overlap, we can just reduce any overlapping instances later on. So we have here a copy to points, and that copy to points takes a second round of points, and we'll use our name attribute to basically spawn a group of points around these ones. So we've got 11. Now we've got 82, which implies that this house will take 82 modular pieces. That's an interesting point that I do want to talk about as well. So when weighing up whether it would be better to have this house as a prefab or as instance meshes, there were a couple of arguments which were draw calls. So if I was to have a house like this with 82 meshes, and maybe the variety is, I don't know, maybe made of 30 different meshes that instance to make the 83 in this case of the house. That's going to still be 30 draw calls compared to just one for a static mesh. So if I had maybe more than 30 houses in the scene, that would start making sense for me to have individual modular pieces. But if I've only got one house, I don't think it's worth having all the individual modular pieces not combined. It also means it's easier once I've generated the house, I can just move it as one solid thing. But then also, if in the random generation I don't like a section of it, it's going to be quite difficult for me to change that. So this is something more later on. So maybe a door or a window that I don't like, or I specifically need a door and a window somewhere. If it did spawn instances, I could just delete the mesh where I want the door and replace it with a door. But that would be for more larger areas, really. Okay, so let's carry on. I've added this Visualise node, and this Visualise node is taking our name attribute and projecting it to each point so that we can see large. Okay, so actually let's take it back here. So we can see that each one of these points have been given a name. We can also see it on our spreadsheet. So we can see these names, and then the points that they're the attribute on. It's kind of hard to actually see the shape of the house. So I could have it shown, but white line. There you go. So now we'll see the difference when we add a bit of points. So all that's happened is now there are just more points added together with all the same names as their parents, because they've received that attribute from their parent, but they have their own name, their child name. So they've got their child name, and then they've also got their parent name. And we basically want to promote the child name to be the name of the mesh, which I think happens here. So then if we look at this one, we've got our parent name, and then we've got our actual name here. So these, we can see here, we've got our index. These 6 are now these 6 meshes here. Now we can tell that because we have 2 walls, 3 roofs and 1 floor, that this is probably a corner top piece. So we've got the 2 adjacent walls. We get another paint. So we can tell, because we've got 2 walls, that we're probably getting something like this. So we got wall, wall, and what does it say? We've got a floor, that's in here, and then we've got our overhang, and then we've got piece. So we've got a roof and a roof like this. Oh my god, sorry, I'm drawing with a mouse. And then we've got a corner piece here, which is important. Okay, so I could probably do the same with the other one. So this one has 6 points as well. It also has a similar layout, so this is probably another corner. I'm presuming this is maybe the spire. What's this one? It's got a lot of points. So we've got 4 walls, 1 floor, and 4 corners. So this is going to be the probably the very top of the spire, where we've got walls all the way around, and then corner pieces, 200 centimeter corner pieces all the way around. Sorry if I'm not really sure how much detail to go in. So now we've got our different sections. So we've got our wall randomizer section. We've got a part for adding arches. Now this is a part of the HDA that I made, didn't use because I didn't have time to make the bespoke arch meshes. These are just extra detail to add to the roofs, and I think because of the angle of my gameplay, removing them, or well, not making them, didn't really make a difference. So I still have the points there that I can call on if I end up making the meshes. I would just need to make the meshes. If I plug the visualizer in, we can see we've got arch 4B, 3B, and 3B. And if we come into the scene view, I'll tell you what's probably generating here is that we'll have our roof, and it will have a cool shape on the top. Something like this. Maybe we could get a cool dragon on the top. And then same here, so we'll have this wall coming down and a roof coming along, and then we'll have that top piece here as well. Yeah, there you go. And one here as well. So there are things I want to add later on. I just need to actually make those meshes because I do want them to be like really nice and ornamental. So let us stick that in and small and zoom in and kind of get a look at what we're working with. So we have walls here that are all just basic walls with no surface information, so no windows, no doors. They're all just flat meshes that are making up the structure of the house. Now, if I swapped this one to be a window, it wouldn't affect the structure of the house in any way. It just means that I need to put a window mesh there. So what we can do is I'll go to the end of this section and I'll plug in the visualizer, and so we can see that this one has now become a window variation. We've got, if we can see any more, so this is a wall with holes in. Got, that still stayed the same. Wall with a door, probably some up here as well. Wall with holes, and trying to think of a, if I come out here, take our wall seed and change what the default value is, it might see a change. Not sure if we did. I was looking at the thing. Well, okay. Basically, there is a reference to that integer value, and that is used to power a random choice of wall. So let's say wall window is 0, wall door is 1, wall hole is 2. We then use that random integer value to power a randomizer that chooses 0, 1, or 2, and then maybe 3 as well for no change at all. So that logic can also be used to choose which window. So I think we've got maybe 13 window variations. So we also want to choose which window that is, and that is for, you can see this number at the end. Maybe there's 14 if the suffix. Okay, so then remember I pointed out how the roof will generate a corner, and that's important because these modular pieces stop. The way that these modular pieces are made is, imagine you have a sausage and you want to make it longer. You can get another one, cut the middle piece out, and then you make a cut in the middle of your sausage, and then you can move that there, and now you've got a really long one with this modular middle piece. I hope that makes sense. That's how the roofs were made. So I basically made one long roof with 2 ends and a middle, and then I cut it into sections so that I could basically repeat however many middle sections as I wanted to get longer and longer roofs. So this piece here is one of the middle sections, and then we need to make a bespoke end for when our sausage does something else. So we have then got our walls. Now this wall is a flat plane, this wall is a flat plane. They are very accurately measured and modeled and positioned so that this corner is flush. Like you won't see into the building, but then you won't have a bevel on this edge. So we want to basically make another mesh which hides this sharp edge, and that's going to be our beam. So we've got our frames and pillars. So now there are more meshes that need to be instanced using points. Now, an important thing to note for this one is we can't see it right now, but if I change the generation real quick. So right now we're working with a generation where there should not be any support pillars. But if I maybe added another box, and this box is gonna be this. Let's just quickly check that it actually generates points. Yep, so we've got and we've done it again, so we've got 0, 1, 2, 3, so that's this shape, and then we've got 4, 5, 6, 7, that's that shape. We've got 8, 9, 10, 11, 12, 13. Now you can see how as we're changing the shape and making it bigger, we're going to get more points, which means that each one of these nodes that are running over the points is going to have to do it more. And even though they are incredibly fast, it does stack up. So if you end up with a house that's made up of like 80 points, it's a giant house, this generation is going to take a while. Okay, so now if we come to the visualizer, we can see here where there shouldn't be any meshes because we haven't got a cube there. We do. We have 2 points per corner, and that is because we are spawning like a concrete block at the floor level, and then a pillar above that, which instances into that eclipse into that concrete block, and then we stretch that point so that it reaches the bottom of these meshes. Yeah, so that's an important thing to note. So that means, so the way that works is that if I come back into MS, is there like a button to clear my canvas? Got a layer. Delete. Whatever. I'll draw on this one. So imagine we have orthographic house here, and this is made out of 4 cubes. So we've already gone and given this a wall, we've got some roofs. And then now, how do we know that this is a roof? How do we know that this one down here has a floor? How do we know that we shouldn't put a wall inside the building? Well, it is because of how the neighbors are organized. So if I have a point here and we have no neighbors this way, we have no neighbors that way, we do have a neighbor in this direction, we have a neighbor in this direction. So I don't know if you saw, you might have deleted that attribute. I can go back. Yeah. Where's our get neighbor? There you go. So this these values here are basically telling us where our neighbors are. So if we come back here, we've basically gone, all right, no neighbors, yes, yes, and yes at the back here, and no at the front here. So we know that this has to be a corner. Because there's no neighbors underneath, that must mean it's one of 2 choices, either the bottom of the building or it's floating. So this point up here has got the same exact thing. So we've got neighbor, neighbor, neighbor at the back, no neighbor at the front, no neighbor at the side, no neighbor underneath. So how can it tell that this one is floating and this one isn't? So we get the bounding box of our whole shape, all the points, and we say this point is our minimum point, and this point is our maximum point. Now it then reads this and goes, okay, is that point at the minimum? Yes. Okay, that means it must not need a support because it's already on the floor. As this point, is it larger than the minimum? Yes. Okay, that means it's floating, so we need to put a support underneath. And then where do we put the support? We put it at the minimum point. So that means we know, okay, that's also touching the floor. I really hope that this diagram makes sense. I am using so you can see how these points are all along a line. Okay, so we can also use this. See the orientation. This is the normal. So these frames are being made in this direction. Now these frames are being made in that direction. That's important because that's going to be how they're orientated. Okay, let's carry on. Now this is where it's going to start getting a little bit hard to look at. So right now, see how we still have our supports here, and now we've got the combined supports with all of the wall and roof meshes, and this is where we're going to start preparing it to the instance. You could instance it now, but this part of the tutorial going forward was making it compatible with Unreal Engine. I did make all of the parts because before finishing it, there's not a proper way that I would know what I could keep and get rid of. So we can skip this bit. I'll go into a little bit. So these attribute wrangles, one of them is a debug that I've made because if I'm being honest, another reason that I didn't actually get this into Unreal is because it would never load. It wouldn't load the building, and I wasn't sure why. And I think it came down to a licensing error where I wasn't allowed to commercially use the HDA outside of which meant that Unreal didn't work. And this is kind of what proved it, was that I debugged that it was checking to instance meshes in the content folder, and it was looking for them, and it was running the string, which confirmed that each one of these points should have been getting instanced from that content folder. But we could tell it didn't work because it not only didn't instant the meshes, but it didn't even create Houdini debug blocks in Unreal, which meant that the HDA just wouldn't have worked. Now that's something as a stretch goal that I want to get working for the degree show, but for now that's not. That is not something I can get done for hand in, because it might just mean that I have to remake this at uni on the proper licenses. Okay, so yeah, that's basically it. So now we have our points. They're all named. We've just as a quick debrief. So they have all been orientated. They've all been scaled. They've all been named correctly. I probably said that one already. And if I was going to improve what is here. I think the first thing that I would do is change the pillar generation. So I didn't realize this until the actual Unreal part of texturing the building, but our plan the whole time for the pillars was well-aligned materials, because there is one mesh getting extremely stretched. If I had this 10 times taller, it'd still be one pillar that's going all the way up. And world align, I don't think is going to be good for my scene. It's not very optimized, and I would prefer it to actually change to be procedurally unwrapped, which is something I can do. I just need a trim sheet that it can unwrap to, and I think the way that I would set it up is by having, let's say we have a box, and this box is our pillar. It's got a long thin pillar, and then we auto unwrap this, and we can look at, oops, wrong button. There you go. So we can look at the UVs here, and I would unwrap so that all of the sections were their own shells. So we want to get the merge threshold down. There you go. So now they've all got their own shell, and then the main thing is, now if I plug in a texel density, this might do exactly what I want, and that is make a really long line. Now you could probably see kind of where I'm going with this. So if my trim had this section be that would face, and it's correct, then this wouldn't be an issue. And if that was the end pieces of my wood, then it wouldn't be an issue. But now if I change the box and scale the box down, we can see that past a certain point, there you go. So it isn't consistent. So what we can actually do, instead of doing it like this, we I'm just going to check that my mic's still picking me up. Yes, it looks like it is. So instead we can actually put a for each connected piece here, which makes a connectivity node. That connectivity node gives us a class attribute which we can reference. So where am I putting it? I want to put it on primitive. So we want it to be for the UV. So each primitive has its own class attribute now, and if we plug in the texel density, what has happened is it has done them all individually. So now it hasn't made one really long row, it's made small and long. So anything that's below the 2 meter limit of my 2048 is now here. Anything that's above the limit of my 2048 is now there. So you can say, yep, cool, you're done. But then again, if I bring this box in past a certain point, it's still now in the wrong section. Let's say I always want these longer ones to be on the same row as this one, even. We can make it so that it gets the bounding box data. I don't want to write that attribute wrangle right now, but if we get the bounding box data, we can basically say is this face, and we'll do it inside of the textile density. So we'll make a group of all of the primitives that are long, and if it is long, then we will move them up by however much they need to be in the right section. I'll go through that in a different video, but that is the logic that I would want to change for the for how those pillars generate. It's just difficult when this again is just supposed to be making points. It just outputs points. So it's not like it's outputting a pillar and it's been stretched. It outputs a point with, if we look at point 116, we scroll down, point 116. So we've got, trying to think, here you go. So we've got scale, 3 meter tall. So it is just scaled it upwards on the y-axis by like 4 meters. So if that was an unwrapped pillar, the textile density is just going to be completely wrong. So it does need a waterline. So if I could change it, it might be that, yeah, it doesn't do it like this, and it does change the unwrap afterwards, but then that would make a bespoke mesh, which is maybe another point for prefab house. Yippee. Okay, thank you. That has been explaining the WFC solver. I think I remembered Mike asked me something about, maybe it wasn't Mike, somebody asked me about this like early on while I was still learning and going through the tutorial, and they saw that it was named WFC and was like, is this I think, what's it called, a wave function command, something like that, and I had no idea what they were talking about, but since then I did my research, and apparently here's a little trivia for the end. This type of generation was inspired by I think it was like quantum physics, or the idea that I think it's like an atom can be in any state until you observe it. So that's the same idea with this pattern. These points could be literally any points until we choose one, and then once we've chosen one, that kind of chooses all of the other ones, because they have to piece together, which I think is quite cool. So I will leave on that point, and my next video will be going through the sine graph. Thank you.